And since it's long, we probably won't get through it all, but that's fine because there's always Friday. So today, I want to wrap up the semi-join and anti-join discussion that we had. I said that these are very useful for translating these membership operations or existence operations in SQL. And so a lot of databases use them, in fact, very heavily. So in, not in, exist, not exist, we're not talking about any, some, and all because I hate them and never use them. And they also make life much, much more complicated. So we had the semi-join, which we wrote as a bow tie missing the right line. Collection of all rows in R that can join with some corresponding row in S. We don't include S's tuples. We just include R's tuples. And the result can never be larger than the number of tuples in R. Like, we don't duplicate any tuples in the semi-join operation. Now, you may have multiple tuples in R that have the same values, but that's because R is a multiset now. But we don't duplicate any tuples. And then we had anti-join, which we wrote as a right-pointing triangle, which is basically all tuples in R that join with no rows in S, no tuples in S. And the nice way of that this is specified is that we have a generic join predicate. So this join predicate can be whatever we want. We could do a natural semi-join, a natural anti-join. We could do a theta semi-join or a theta anti-join, whatever join conditions we prefer. So we introduced that last time, and I want to give you a couple examples just to show you that it works. And then when we get into planning and optimization, we'll actually talk about some of the more sophisticated things going on. This is the kind of query you might see on a homework assignment or an exam in CS121. Find all the bank customers who have an account at any bank branch in the city they live in. And just as a little reminder, remember that branches have a branch name and a branch city. So in the inner query, you can see that we try to find all the branch cities for the current customer. So is this correlated evaluation? Sadly, yes. It is correlated evaluation because we refer to the enclosing query's customer ID. We use that to select out, notice all the depositor is used to find the customer's accounts, then account is used to find the branch names, and then branch is used to find the branch cities. So we have to do this three-table join just to identify the branch cities that correspond to the customer city. And you can see as well that correlated evaluation would be the kind of thing that would make you want to shoot yourself in the head. Because we have a three-table join occurring for each row in customer. So you have 10,000 customers. Let's say you're a little credit union or something like that. You're very sad. Any questions? Everybody see how horrible this is? So this is a bad query to execute in a correlated manner. It turns out that it's actually a challenging query to execute in a non-correlated manner as well. And we will revisit that topic, but that won't be the discussion for today. Now, what we can notice is that instead of computing each customer's branch cities for that customer, why not figure out the correlation of customers and their branch cities all at once for all the customers in our bank? And so you can see that we've extracted the inner query, and now we just say, tell me customer IDs and branch cities. You can see how mechanical this translation could easily be just based on the correlation predicate that we have here. D.customer ID is C.customer ID. So we go ahead and include D.customer ID so that we can now do some kind of join. And so that inner query is now going to generate tuples for each branch, like I say here, that each customer has accounts at. So we can use this as a building block. We could, for example, use an on clause to join the inner query's results to the outer query. So now we have select c.star, which is valid SQL. We could write that. I don't think NanoDB supports it because I have a parser generator error that I still haven't solved to this day. But anyway, you do this to select only the customer parts of the results, and you join customer against this collection of branch cities and customer IDs, corresponding customer IDs, based on the customer IDs matching and the customer city being the branch's city. Is this correct? Do I have any problems? CS121 TAs, you'd better identify them. Now I've thrown it down, huh? These kinds of decorrelations actually are quite challenging, and there can be very subtle bugs in the translated version. It's funny because there was this guy who wrote a research paper. I can't remember when it was. I think it was like in the 80s, like the late 80s. And he said, you can decorrelate this kind of query in this way. And there was a bug in his approach, in his solution, that was not discovered for like 5 or 6 years. And somebody wrote another research paper saying, actually, this approach is completely flawed, and we can't use it at all. So here's a better solution. So this kind of thing is subtle. Do what? The second one, nobody has found problems with yet. So yeah, evidently we're okay. But yeah, once you sort of identify the form of the errors that can occur, then you know to look for them. Like in this situation. The question I would ask is, how many times does each customer appear in the results? Versus, how many times should each customer actually appear? How many times ought they to appear versus how many times do they appear? What if a customer has multiple accounts at a bank branch that's in the same city that they live in? How many times will that customer appear? This is the issue with joins. Joins can duplicate rows. But in clauses don't duplicate rows on the thing on the left of the in. And that is a mismatch in the way that we have translated this thing. So if we have a customer with multiple accounts, the outer join duplicates customer rows if I have multiple matching rows in the inner query. That's why we can't just do this with a regular join. Now, thankfully, we just introduced a tool that we can use to solve this problem. Instead of using just a regular join, we use a semi-join. A semi-join is going to use the left, it's going to basically keep the left tuple once we find any tuple on the right that actually joins. But we're not going to duplicate left tuples based on how many times they would join or how many rows they would join with on the right. Okay? Does that make sense? So semi-join is our friend. So we have this original correlated query. I'm going to be lazy and not actually draw an execution plan for this yet, just because I didn't want to be up till 2 a.m. So, but you can imagine how you would do this. Some databases actually allow you to write semi-join like this, but not many. There's a very few databases that actually allow you to do this. It would be kind of fun to do this in NanoDB, but I think it's probably more interesting to just try to do standard SQL and translate this in your planner optimizer. Yes? What if you can't decorrelate it? So this is the thing that you run into a lot with databases. The planner optimizer will be oh so smart, but no smarter. And so you run into situations where you cannot decorrelate. They do happen. If you have non-equality, so again, you see how this correlated query is written, where d.customerID equals c.customerID. That's the correlation. And it's an equality correlation. If we have an inequality correlation, it is much more challenging to decorrelate those things. In those situations, you just fall back on correlated evaluation as I described it in, I think it was last lecture. So you do the whole thing of, oh, I've got a big ugly subplan hanging off my where predicate, and I reset the subplan and evaluate it and compare the left side to the right side. Horribly slow, we're very unhappy. But thankfully, probably 95% of these subqueries can be decorrelated because they use equality conditions. So intelligent databases, which most widely used databases, are very intelligent now in doing this. Back in the late 90s and early 2000s, it wasn't that way. But you all live in a world where databases can decorrelate. One more thing to be thankful for, I guess. Anyway, any other questions? Let's see. Yeah, that's what I just said. Now here's another one, just to illustrate exists and not exists. So this would be an example of where anti-join would be helpful. So you have select star from customer C. I want to find all the customers who have no bank branches in their home city. So That's a much easier query because I don't need to look at accounts or depositors or anything like that. So I just say select star from branch B, where B.branch city is C.customer city. And you see this a lot. When you have an exists or not exists, don't do a project in the subquery because that's a waste of time. Just say select star because you just want to find out if there's rows or not. And this means the database does as little work as possible to find whether or not there's rows. So you want to see if there are, basically the inner query generates no results. If it generates no results, then we want to include the outer row. If we do no results, then clearly an anti-join would be a great option. Okay, yeah, and like I say, your correlated evaluation wouldn't be nearly as horrible in this situation because we don't have a 3-table join we're doing that could be really horrible and all of that kind of stuff. If you had an index on branch city, correlated evaluation would probably actually be quite fast. Now, decorrelated evaluation is still going to be much faster, but little queries like this are not horrible. So like I say here, what you're effectively doing with exist, not exist, and in and not in is you're doing a join, so why not actually leverage our clever join algorithms, which we're going to start talking about today. So we could write this with an anti-join. So notice, again, I'm being lazy and writing this with SQL instead of writing a plan. I will probably have plans drawn up for when we talk about optimization of these things. But select star from customer C, anti-join branch B on branch city equals customer city. And the anti-join will only include rows from the left-hand side. This is a left anti-join. It will only include rows on the left-hand side that do not join with anything on the right-hand side. Okay? So you can see that this is a decorrelated version of the exact same thing. An anti-join can be implemented very, very efficiently, particularly if you're doing like a hash join algorithm or something like that. And it'll be much, 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 much faster than the original correlated version. Okay? Now we could also do this with an outer join. And it's kind of interesting because we have multiple options when we translate these things a lot of the time. So here we have select C.star, which again is valid. From customer C, left join branch B on branch city, customer city. Where branch city is null. Because remember, we're doing a left join, a left outer join. So customer rows will be included whether or not they have a corresponding branch row. And if you have a customer that doesn't match anybody, the corresponding branch row will be nulls. So we can just say if branch city is null, include it. And like I say here, the approach doesn't generate duplicates this time because if we don't have any matching row, we're only generating one output tuple with C's values and nulls for B's values. So we can use this approach. But is the second or the third version going to do more work? Consider do more work in terms of generating rows. Again, imagine a situation where a customer has 10 accounts the customer has 10 branches that are in the same city as the customer. Each customer row that customer's row would be duplicated 10 times. So we can see that the third query would actually generate more intermediate rows that have to be considered and discarded than the second version would. So lots of benefits from using anti-join as opposed to outer joins. Okay? Now there may be other reasons why we would want to do this with an outer join, but we'll start exploring some of those things when we get to planning and optimization. Yes?
So with the anti-join,
the anti-join basically is implemented so that it does not join tuples together. Like it will never generate tuples that are C's values unioned with B's values. So it doesn't do that extra work. Also, if it sees that anything matches, it automatically skips the left tuple. So it doesn't generate any intermediate rows at all for things that match, which the outer join would generate intermediate rows for things that match. Okay, does that answer that? So you can see outer join is, it's designed for a different situation. An anti-join is kind of a really special case, but it is so useful that it is totally worth having that special case supported. And that's why, for example, you get on Oracle and you write exist queries or not exist queries, and tell Oracle to explain itself, and you discover that it's plugging in anti-joins and semi-joins all over the place because it's just faster. Okay? So there's a couple of examples. Just to wrap up this particular topic, like I say here, this is just like the barest introduction I can't even tell you. And I have probably 24 research papers on my computer that describe all kinds of approaches and details for decorrelating nested subqueries, evaluating them more efficiently, lifting them up into the outer query, and so forth. So I will try to introduce a little bit of that material to you in a few weeks when we start talking about plan optimization. But you may have to go and look into this stuff yourself because it is so rich. And it's pretty advanced. I mean, this stuff is really only, some of the modern techniques are really only being incorporated into databases over the last 5 to 8 years. Which, if you think about my classes, normally we talk about stuff that's from like the 60s through the 80s. I mean, it may be in modern operating systems now or modern databases now, but we've been doing it for decades. Some of this stuff is really, really new. Okay, so yeah, basic tools for decorrelating, so outer joins, and sometimes you have to do grouping and aggregation if you're using this technique for subqueries in the select clause. That tends to be where you need grouping and aggregation. Semi-joins and anti-joins for these membership queries in where clauses, having clauses, and so forth. But there is another question that we need to think about, which is how do we know that our decorrelated version is actually better? Or if we have multiple options for decorrelation, how do we know which one is actually better? And we will start talking about that hopefully in about 2 lectures when we start talking about plan costing. How do we actually estimate the cost of an execution plan so that if we have 2 or 3 to choose from, we can choose the one that's actually best? Okay? Any questions about nested subqueries before we boot this topic? We're ready to move on. Okay. So we're going to start talking about implementations. We had these things that we had enumerated we needed to deal with if we were going to evaluate SQL queries. First one, implement relational algebra operations in some way. We have not talked about this yet. How do we do this? The second one was how to translate the SQL abstract syntax tree into some kind of plan. Well, we've kind of beaten that one to death pretty well. That we have a lot of options now. They're all pretty naive, but at least they'll work. And then finally, how do we evaluate this execution plan we come up with? And there are a variety of ways, but we decided to do it with this pull-based. So you ask the top node in the plan, give me your next tuple, and the top node turns around and asks its children or its child for tuples. And so you just repeat this to generate tuples. So it's pull-based and it's pipelined. We do not materialize the output of every plan node during the evaluation because that takes a lot of memory or disk space and generates a lot of extra I/O. So we need implementations. That's what we're going to talk about next. Now select, super simple. If I told you to implement select without giving you any more information, I bet you could do it very easily. This is why I actually give you the select implementation because it's kind of unexciting to write. So like I say here, retrieve tuples from the child plan node or from the table if it's a file scan. And you keep doing this until you find that your selection predicate is true for whatever tuple you're considering, and then you pass that tuple up. And that's all you have to do. And of course, the select plan node, to be nice and generic, can have a missing predicate or an unspecified predicate if you just want to do a full table scan. And so that unspecified predicate is the same as saying true. And of course, like I say here, there are several different kinds of select plan nodes based on where tuples are coming from. The way that they are described in NanoDB is you have file scans, which is a common term. It's not NanoDB specific. File scan through the entire table. There's no children. You just say, here's the table name. Open it and give me the first tuple. Now give me the second and the third and so forth. And then you have simple filters, which are selects that don't operate on a table. Now you can say to yourself, well, why not combine file scan and simple filter? You could. I just thought it was a little bit cleaner to factor them apart. Some databases probably combine them together. You could also have index scans, but since we pretend you don't know what an index is yet, because we haven't talked about it in 122 yet, but doing an index scan is another technique if, for example, you can evaluate a grouping and aggregation entirely against an index, or if you want to do some kind of index-based join, like index-based sort-merge join is really powerful. And again, we haven't talked about sort-merge yet, but you'll start to see how indexes can be very helpful. So index scans would be another kind of select operation we may want to perform. Now there is one optimization that is worth mentioning, which is that if your selection predicate is doing an equality test on the key attributes of the source, then guess what? You can stop when you find your first matching row, because there are no more matching rows. The presumption is that the key columns or the key attributes functionally determine everything else that the child plan node or the table is going to produce. So there's no reason to keep searching. And this is a pretty common situation. Think about how many times you might, if you were writing a web app, I need to pull up customer Jones's information. Or I need to find out what cars Jones owns or Jones has insured. Or I need to find out what books Jones has bought. So there's a lot of situations where you do selections based on a key, and you basically can stop looking after you found the first row, because that is the row you're looking for. Okay? So pretty simple. Any questions at all on this? Select is so simple. Okay? Now project is equally simple, except that project is actually a much larger pain in the butt than selection is. Because you have all of these expressions, basically, that you need to evaluate to generate output tuples based on the input tuples. So just to give you a few details on the mechanics. Again, project is one of those things, A, you don't learn much from implementing it, and B, there are some annoying complexities of it, so I give you a project implementation. You don't have to do that in NanoDB. But you can see, as I have here, that basically the schema of the child plan defines the environment that the expressions in the project are evaluated in, the context of the expressions. And then tuples, as they come up, specify the values of those variables. And so when you when you evaluate predicates, you evaluate them in that context and generate results based on the input tuples. So very straightforward. Now the one thing to mention about both selects and projects is that they both can have subquery if you have not decorrelated things or you haven't found some way of extracting those subqueries. So if we have a situation where we are stuck with some subquery, then you have to think about that when you're trying to figure out the select or the project's cost. Because naively, project's cost will just be, the same cost as the subplan, except I need to process each tuple. So there's additional CPU cost. Selection, again, well, I have to scan the table, or I have to scan through all the input tuples from the subplan. So my cost is pretty straightforward, unless I have a subplan I need to think about. Okay? So we'll get into that, but you just have to be aware of that one little tiny wrinkle when it comes to select and project. Grouping and aggregation. Again, straightforward and a pain in the butt. So I give you guys both of these grouping and aggregation implementations. You saw how much annoyance there was with translating SQL into an execution plan. So that's enough for you guys to deal with. If you have a situation where the input tuples are sorted, they're in sorted order based on the grouping attributes, then you can implement grouping and aggregation with sorting. And this is the most resource efficient way of doing it, because you know that all the tuples that fall into a particular group are all next to each other. And you can just traverse the tuples in order and generate each group in sequence. This turns out to be a non-blocking grouping and aggregation operation. So this is just a description. For each input tuple, you compute the grouping attribute values. If they still match the existing group that you're considering, then the group is completed, and you generate an output. Sorry, there's something in my eye, and it's really freaking me out. Anyway, so you output a tuple with the current group's values and the aggregates you've computed, and then you start a new group. But if the grouping attribute values haven't changed, then you just go ahead and incorporate the tuple's values into the aggregates you're computing. So very straightforward. I have a sketch of it just to show you some pseudocode for it, and also to get you warmed up on this, because we're going to be looking at a lot of pseudocode for the next couple of lectures. So current group is empty, so we start out with that initially. Current aggregates is also empty. And we get the next tuple from the sub-expression E. That's why we call it E, because it's just a sub-expression or a subplan. We compute the grouping attributes from tuple t. So we figured figure out what the tuple t's grouping attribute values would be. And if the input tuple was either null or the grouping attributes have changed from the current group we're considering it, then we go ahead and output a tuple for the current group that we're just finishing up. We update the grouping attribute values to be the new group that just started, and we reset all of our aggregates. Once that's done, we go ahead and add tuple t into the current aggregates. And we just repeat this until we consume all of the tuples that subplan E produces. Does everybody see how this works? This is a rough sketch. This is not precise because, well, there's not a lot of value in having, well, if t is not null here and if t is not null there, and it just gets tedious. So we just have a rough sketch of it. Yes?
So the first thing when implementing grouping and aggregation is to sort whatever you have and then multiply it.
Well, that is a very interesting question. Is the best way of doing this to sort the input tuples? Sometimes that may be faster. It's funny because that's actually what MySQL does all the time, is it sorts the inputs. You may have noticed that, and you may have lost points over this, and for that I understand your pain, that you do an order by and you don't specify, you specify group by and you don't specify an order by, and magically the results come out in order based on the grouping. Because MySQL does sort-based grouping and aggregation by default. You have to write something crazy like group by null in MySQL to get it to do hash-based grouping, which is weird, but that's just the way MySQL works. But so yeah, that's one possibility. The other possibility, like I said, is that you may be computing a grouping and aggregation operation that can be satisfied entirely from an index on a table. If all of the necessary columns are in that index, then you already have them in order. And so, boom, you're done. There's another possibility that you may be sorting or you may be grouping and aggregating on the result of a join. And a sort-merge join may have been used for whatever reason. And so again, the tuples are already in a sorted order. So you can use the sort-based grouping and aggregation more easily in those situations. So I suppose it would be worth considering sorting and then doing a sort-based grouping and aggregation in your plan evaluation, figuring out which plan is the fastest. But in general, the sort-based grouping and aggregation is used because tuples are already being produced in sorted order because of something else happening upstream, if you will. Okay? Any questions about that? Did you have another question? Okay, yeah. So that's basically the idea here. Let me see. So aggregate functions, just to touch on this, I don't want to get too far behind, but aggregate functions, they work a little bit differently from simple scalar functions like mathematical functions, where I give it inputs and immediately it produces an output. We have plenty of those. You can see those. There's a whole functions project or sub package in NanoDB with dozens and dozens of functions implemented for various things. And if you see other ones that would be neat, then add them, and then you can tell us, and we'll incorporate them into our full implementation. Aggregate functions are a little bit different because they have to consume a sequence of inputs and then ultimately produce the aggregate. So I have an example here of min. Very obvious implementation. You just keep feeding it values. If the input, if x happened to be null, ignore it because aggregates are supposed to ignore null inputs. And so you keep feeding it values and it just keeps updating its internal state of the minimum value it's seen. So, and then when you're finished, when the group is done, then you go and ask the aggregate function, okay, what was the aggregate result? And then you use that to generate the final result. So you can see that aggregates work slightly differently from regular simple scalar functions, which is kind of neat. There's basically three different kinds of functions you'll see in database implementations. There's the simple functions, there's aggregate functions, and there's table returning functions, which are the coolest of all. Because if you can plug in your own implementations of these, like you could add your own aggregates, it would be no problem. But you can also create table returning functions, and if you have the ability to put a function in your from clause, now you can have some real power to do whatever you want. You could have that function connect to another database. And now you have an easy way of implementing parallel plan evaluation in a distributed system of database engines, just by having table returning functions that establish connections to other databases. There's so many things you can do. You can use that to aggregate from multiple disparate database systems that are different vendors or whatever. This is very common in the commercial world, working with commercial database companies who have multiple systems that they need to integrate. So there's a lot of really cool things you can do by extending this whole notion of what functions are allowed to do. Yes?
Is it possible that there's an aggregate function that can do anything until it has every single one of these?
Is it possible to have an aggregate function that can't do anything until it has all of the inputs? I would argue that min and max are that way.
Well, we can get it, for example, if each one of those
Yeah, so you can definitely update the current minimum as you go, but you don't know you don't know the right answer until you've seen all the inputs. But I think I understand what you're asking. I think that count distinct is a good example of where you have to see all the inputs. You don't really know. I mean, again, along the way, you can say, this is how many distinct values I've seen so far, but you also have to keep track of everything you've seen with count distinct. So count distinct is kind of a painful one to implement.
So the little function that we showed before would be a very bad function.
That's a good question. Do you mean the sort-based aggregate? Or okay, well, sort-based aggregate, like if you have your inputs ordered on the column or the set of columns that you're doing count distinct on, you can again evaluate that very efficiently. It's only when they're not in that order, and you have to do a hash-based implementation where it has to keep everything in memory. Yeah, ordering saves you a lot of time and resources in a lot of different situations. Yeah. Okay, you guys have successfully distracted me a lot, so I'm going to try to hurtle on. So if we don't have sorted inputs, then we have to do a hash-based implementation where basically the plan node maintains some kind of hash table in memory. This hash table may have to spill to disk. This is one of the unfortunate realities of hash-based grouping and aggregate computations. Because we don't know that we've seen all the tuples for a particular group until we've seen all the tuples. And that's just the problem with hash-based anything in database systems. Okay, so this is what I was just describing. You'd need some way of spilling over to disk. Now, just as an aside, NanoDB does not require any external memory anything. So you don't have to worry about implementing that, although if you wanted to do that for CS123, that would certainly be something you could do. Okay, so here's a sketch of the hash-based grouping and aggregation implementation. So we have our mapping of grouping attributes to aggregates. And you can see while E has more tuples, get the next tuple, compute what the grouping attribute values should be, use that to look up the corresponding set of aggregate functions, update those aggregate functions, and then get the next tuple. And you can see here how obvious it is that this is blocking, because we have to do this for all of the tuples that our subplan produces before we can then go and generate our grouping and aggregate results. So we have a second phase at the end that generates our actual output tuples. Okay, any questions? Okay. I just wanted to mention as an aside that this little join thing means concatenate two tuples together and create a new tuple, which is kind of unfortunate because earlier in describing semi-join and anti-join, we used join to indicate the predicate. So just make sure it's clear in your mind that this join means something different. You'll actually see this as we start talking about join algorithms. Okay, sorting, very straightforward. The only challenge is when things don't fit into memory, in which case you use an external memory sorting algorithm, and it is as straightforward as you could imagine. We read in as much as we can, we sort it, and then we write it out. Then we read in as much as we can, sort it, and write it out. And we generate all of these run files from our input data. And then once we've done that, then we can start doing a merge sort, an n-way merge sort on all of those input files. So here's the first stage, create n-sorted runs from an input tuple file, while the input file has more blocks. And we're presuming here that we're reading it from a file, and it's a reasonable presumption because we're saying, well, maybe this doesn't fit in memory, so we have to read it from a file. So we read up to some number of blocks, sort the tuples in those blocks, and then write that out to disk. So since this is an I/O intensive operation, it makes sense to do this against disk blocks. And of course, if we can load the entire file in, then we're already done, right? Because we have sorted things already, and we can just feed that out to whoever wants the resulting sorted results. Now, second stage is merge the n-sorted runs. And this is where it gets a little bit tricky, because you can see we open all n of our run files, and we read the first block from each one of those run files. And then we go through all those blocks, and we find the earliest tuple in the output, based on the sort order that was specified, from all the blocks that we currently have in memory. We write that tuple out, and then we go past it in that block. If we advance through that block, then we have to load the next block. So that it's kind of a neat thing that this is only going to require n blocks of memory from the buffer manager to sort these n giant data files, because it's a merge sort. Okay? Now we just keep doing this until we run out of blocks for all of our input files. Okay, any questions on this? It's pretty straightforward. The one wrinkle is if we have a situation where our input table is huge. Like, let's say that it's multiple terabytes. Thankfully, I've never had to deal with a file that large that I had to sort. But the problem is that we may not be able to actually do this n-way merge sort because n is too large to open that many buffer pages for that many files. Now, again, this is probably not realistic these days because of how much memory you can cram into a computer. If you're curious, there's actually there's a sort benchmark called penny sort, and there's another one that's like called minute sort or something like that, which is how much data can you sort for 1 penny of compute power and time and all of that. You'd have to look at the definitions to figure out how you are allowed to compute that 1 penny's worth of computing. And then there's minute sort, which is how much data can you compute in, or can you sort in 1 minute. And this is one of these competitions that people have. So they try to create cache-friendly sorting algorithms. They care a lot about I/O because they can sort way more data that can fit in memory. So these kinds of things happen, but they tend to be infrequent, I should say. Anyway, this approach is straightforward because even if we can't fit all n, a block from all n run files into memory, we can just go ahead and sort a subset of them and generate a new run file from those, and then obviously throw those out, and then do that again and again and again. So we collapse things down in multiple steps until we can finally do one merge sort pass that can generate results from everybody. Okay? So just repeat, it's like they say on shampoo bottles, rinse and repeat, and you'll achieve your desired results. Now, there's other reasons why we might want to have fewer sorted runs, because imagine that I do have, let's say, 500 run files, and if each one had like 4K disk pages, then you could probably do the math. It's not going to be that much space that it would require. But the problem is, I'm reading from 500 run files. Think about what that means in the context of these spinning magnetic disks. I'm reading one run file, then I have to jump and read the next block from this run file, then I have to jump and read this disk block from this run file, and so forth. Disk seeks become horrid in this situation. So what makes more sense? Generate fewer run files and make them larger, and then read more than one block from each run file when you're reading data into memory. Even just making this little change makes your sorting so much faster on a magnetic disk. Now, you don't need to do this on a solid-state drive, but on a spinning magnetic disk, this makes a huge difference because you're eliminating seeks. Disk seeks are the slowest thing that a disk can do. Okay? Any questions? Just wanted to mention that. Okay, now, for the next few lectures, we're going to talk about joins. Like I say, it's a little bit complicated, but when you see a join algorithm that looks like this, how can you hate it? It looks so gorgeous and pretty. For all the tuples in R, then you go through all the tuples in S, and if the predicate says these two tuples match. They were made for each other. Then you go ahead and concatenate them together and send them out the door. It's love at first sight. This is nested loop join. You can nest this as much as you want for as many tables as you want, which MySQL makes immense use of because they do an n-way nested loop join for their join processor. The nice thing about this, it works for any predicate you could possibly come up with. Non-equijoins, they happen, rarely, but they happen. Any complicated stuff with like is null in there, it's like, why is anybody doing this? But if you have non-equijoins, and you do from time to time, then nested loop join is a really useful mechanism for evaluating those things. Now, what's the drawback? How many times do I traverse the inner table? Yeah, well, so we have a couple of different sizes we need to think of. You're thinking in the right direction. We have the number of tuples, and we have the number of disk blocks. And we'll start talking about this more next time. But we traverse the inner table once for each tuple in R, which is horrible. Very, very slow. This is another reason why I like to force people to flush the buffer manager every time when they're implementing nested loop join, because you get a real appreciation for how horrible it is. If you're able to sort of collapse down the amount of memory that the buffer manager is able to hand out, you see these effects as well. But forcing nested loop join to run in a small amount of memory makes everybody miserable. It incurs a lot of I/O overhead because of this. Now that was a very straightforward implementation. Let me see. I have the original algorithm here, written in 4 sweet lines of code. How do we extend this to do left outer join? So we want to include T sub R if it doesn't match anything in T sub S. What would we do to this algorithm to support this? Yeah. Where would we put the else clause? Would we put it after the if? Yeah, think about it. We can only include T sub R in the left outer join as an outer join tuple if it matches nothing in S. Yeah, so that's basically the right approach for this problem. We have to have some state outside to keep track of whether T sub R has been matched, and we will have an inner thing in here saying, hey, I matched something. And then we can look at that after the inner for loop to see if it matched or not. So it would be something like this. Again, pad nulls is a magic thing that allows you to add the same number of nulls as S has columns, or whatever the arity of S is. NanoDB makes this very simple. You can just create a tuple literal and say, I want this many columns, and they're all automatically null. So it becomes really easy. And then you can concatenate tuples together. Okay, so that's left outer join. What about right outer join? So now we want to include a tuple in S if it doesn't match anything in R. Yeah. What if we were stuck in this horrible world, in a world where you can't switch the left and right sides of the...
I mean the for loop.
In the for loop, yeah. So you're saying traverse S in the outer loop and R in the inner loop. Yeah. So that's basically what you have to do, because there's no easy way of changing this implementation to do right outer join. But the nice thing is we have an equivalence rule we can take advantage of. R right outer join S is the same as S left outer join R, as long as we make sure that we do an appropriate project to produce the results in the appropriate order of columns. So then, once we have left outer join, we can easily do right outer join. Okay? So that's that. Now again, what about full outer join? We have the same problem. The left part is fine, the right part is the hard part. We'd have to have some kind of state for every row in R to see if some S match. Wait, no. Every row in S to see if something in R matches, I think is what we'd have to do, and then traverse that state. Prohibitive for large input arrays. So if you're curious why MySQL does not do full outer joins, this is the reason why. Because you can't take nested loop join algorithm and change it to do full outer joins. Any questions? And this is why all the other databases that have more reasonable plan node based internal implementations have no problem doing full outer joins. Okay, left semi-join. This is useful. We'll talk about this with nested loops. You'll see how straightforward this translation is. So we'll go ahead and talk about it with nested loops, and then we'll ignore it for the other join algorithms because it's pretty straightforward. Okay. So like I say here, T sub R is included once if it matches any row in S. Everybody see how to do this? We just have a little bit more logic that we need to incorporate. Yeah.
We only care about the TR.
We only care about the TR, that's right.
So, I mean, add join to result versus add TR to result.
It would be add TR to result. Yeah, we need to break out of the inner loop because now we're done. Right? We're done, I should say we're done with TR. We just go on to the next TR. You know what? I don't think that I actually need the matched thing at all. This is what happens when you write slides late at night. So I will get rid of matched because you don't actually need it. But you see how simple it is to take nested loop and change it to a left semi-join? That is so cool because now we can actually use this to make a planner that doesn't suck. Okay, so that's left semi-join. Now, what about left anti-join? So TR is included once if it matches no rows in S. And I have a feeling my implementation is too complicated again. Yeah, so this is kind of an interesting one. It'd be really cool if we had the ability to continue in the, or tell the implementation to continue the outer loop instead of the inner loop, which some programming languages let you do, but not everyone does. And if you're ever curious why we want to have a version of break label or continue label, this is the kind of thing that would allow you to see how that's useful. Because break and continue apply to the immediately enclosing loop, but you can see that sometimes you'd like it to apply to the outer loop. Okay, let me see what I have here. So TR and R matches false. So if, and this is just accommodating for the fact that we don't have a break or a continue that you can put a label on. So if I find a tuple in S that matches, I record that it matched, and I break out of the inner loop because I don't care anymore. I'm done with T sub R. And then I say if it's not matched, then I add TR to result. And I go on. Did I get that right? I'm honestly asking. I'm not asking because there's a bug in there. I mean, there may be, but I don't know. Yeah.
Are these like the most efficient implementations?
Are these the most efficient implementations? Hell no. We're going to be talking about, but like I said, actually, let me go ahead and do this because we're actually on the last slide, and I wanted to do this. Nested loop join is very slow. But everybody has an implementation of it because it is so useful to have a general purpose join algorithm that handles all the cases that you don't get to handle with your specialized join algorithms. Other join algorithms, we have, guess what? Magic, right? Sort-based joining and hashing-based joining. As always, you'll see both of those general approaches. So those join algorithms require you to be working with equijoins, not arbitrary condition joins. And sort-based joins obviously expect the inputs, or at least one of the inputs, to be sorted. So since we had these constraints, it's really nice to have nested loop join around. So what we're going to do next time is we're going to figure out if we can make nested loop join a little bit faster. We're going to study some of its performance consequences, and we'll introduce the other two very widely used join algorithms in database systems. So, all right, see you on Friday.